So hello guys, in this video what I want to do, I want to find a Jordan form for a 2x2 matrix, and in my future videos I'm going to show you how this matrix is actually connected to finding the certain determinant of n by n matrix and how that matrix is connected to representation theory. But before, let's just try to figure out what is going to be a Jordan form for the following matrix A, which is given by 2, -1, 1 and 0. So the first thing that we should do, we should try to diagonalize this matrix. So as a step 1, let's try to find its eigenvalues and eigenvectors. So the idea, every time we want to diagonalize a matrix, we want to find the corresponding eigenvalues for this matrix and its eigenvectors. And then we're going to use our eigenvectors to form a basis of our space in such way that our matrix is going to be diagonal. So let's find first for this matrix eigenvalues. According to the definition, we just need to find the determinant of the following form, set this determinant to be equal to 0 and solve this equation. So on the left hand side we're going to obtain 2 minus x minus 1, 1 minus x is equal to 0. So my left hand side you can see is going to be equal to 2 minus x times minus x. Minus 1 will give us 1, so plus 1 is equal to 0. So then I will get x squared minus 2x plus 1 is equal to 0. Here I'm going to factor this quadratic equation, so I'm going to get x minus 1 squared is equal to 0. So we can conclude that from here I have the only eigenvalue, which is x is equal to 1. But you can see when we set our determinant is equal to 0, in other words, we're looking for a characteristic polynomial. And for each eigenvalue, we can talk about algebraic multiplicity. And in this case, algebraic multiplicity is 2, because in my characteristic polynomial, which in this case is actually x minus 1 squared, x minus 1 is going to show up 2 times. So my matrix is going to be diagonalizable if my algebraic multiplicity is going to be equal to a geometric multiplicity. So what is geometric multiplicity? Geometric multiplicity, in other words, it's how many eigenvectors I'm going to have for my corresponding eigenvalue. So let's try to answer this question. So to find the eigenvectors for this eigenvalue, in other words, we need to figure out how many vectors are going to span the kernel of this matrix, x minus I. And my vector v is going to be inside my kernel if a minus x times I times v is equal to 0. But in this case, I will have just a minus I, which is equal to 2 minus 1, 1 and 0. And we know that it's equivalent to just to find the row echelon form of this matrix and to see what kind of relation do I have for my coordinates of the v. So for example, what I'm talking about, if v is equal to a over b, then I need to find some restrictions on components of vector v such that this restriction will allow this vector to belong to the kernel of this matrix. So let's do it. And here let's continue our computation. So we'll have 1 0 0 1. So I'm going to get 2 1 minus 1 1 minus 1. And then we can see if I'm going to take the first row, multiply by -1 and add to the second one, I will get the matrix 1 minus 1 0 0. And then since we have this matrix, we can figure out what is our restrictions for coordinates of the vector v. So I will have AB is equal to 0 0. So from here follows that I will get the vector A minus B 0 is equal to 0 0. So then we're saying that my vector v is going to belong to the kernel, or is going to be, in other words, to an eigenvalue, an eigenvector with a 1 as an eigenvalue, if A is going to be equal to B. And how do I know this? If I will take my first component and set it equal to 0, then I can see that A is equal to B. but then, so my b is equal to a, but then a is just a constant, so I can factor a constant. I will get 1 and 1. And from here, I will obtain the only one eigenvector v1, which is exactly equal to 1 and 1. I have another eigenvectors. They're going to be just multiply of 1 and 1. And you can check that if you, for example, take 2 and 2 and multiply matrix A by this column vector 2 and 2, you will get the same vector 2 and 2 times the constant 1. Okay. So right now we have a problem that this matrix is not diagonalizable. Why? Because we have only one eigenvector. So in other words, it means our geometric multiplicity is equal to 1. And in this case, my algebraic multiplicity doesn't equal to geometric multiplicity. So it means this matrix is not diagonalizable. So that's why we need to do step number 2. So what we're going to do for step 2? For step 2, we will try to find the Jordan form for the matrix A. So what is the idea of the Jordan form? The idea is the following, that we start all our previous computations for this matrix A in a standard basis E1 and E2. So what I'm claiming, since our eigenvalue in this case is equal to 1, then I can change this basis, and let's call this basis B, for example, to B prime for some vector like W0 and W1, such that in this basis B prime, my matrix, my new matrix A is going to have the form, let's call it like let's call it G, is going to have a form 1, 1, 0, 1. So I'm claiming that I can find another basis and do the change of basis transformation to obtain that matrix A up to change of basis is going to be equal to matrix G. So what is my claim? My claim is the following. I'm saying that I can choose my B prime to be equal to the eigenvectors that I found before, which in this case is V1, and another vector V0. And what is V0? V0 is a vector which will satisfy the following equation. So it's going to be my matrix A minus lambda I, V0 is equal to V1. So let me give you a couple of reasoning why I'm looking exactly for this V0. And here I want to answer two questions. First, why is this true? In other words, why can I find V0 in this form? And the second question, how I'm going to actually get the block diagonal form. So let me first answer your second question, and then I'm going to show you my reasoning for the first one, why we actually can find this V0. So we fixed a basis B prime, which we just found apparently, which is V0 and V1, and we want to find how a matrix A is going to be look in this basis. Or in other words, we want to figure out what is A of V0 and A of V1. A of V1, we know the answer. It's just equal to 1 times V1. So I have 0 times V0 plus 1 times V1. So in other words, in our matrix, our second column is going to be exactly 0, 1. But what about for the first column? I can rewrite my expression as A minus I plus I times V0. And then what I'm going to get? I'm going to get A minus I V0 plus V0. But then according to this inequality, A minus lambda I V0 is equal to V1. So this first vector is actually equal to V1. And my first column is going to be exactly consist of numbers 1 and 1. And the reason is why, because then I will have 1 times V0 plus 1 times V1. So from here we can see that we're going to get that our matrix G in this case is going to be equal to 1, 1 and 0, 1. So let's answer the first question. And for the first question we need to argue why this V0 exists. But here it is just enough look at the following form. We know that our kernel of matrix I minus I is going to be one-dimensional, and it's actually spanned by vector v1. So in this expression, you can see that it just tells us that v1 belongs to image of a minus lambda I. So what I want to do, I want just to take intersection of my kernel with my image, and then here I have two options. The first option, my kernel is going to be equal to 0. My second option, my kernel is going to be not equal to 0. So we have our first option and our second option. And here I need to discuss a small thing. Since dimension of my kernel is 1, then according to null rank theorem, then dimension of my image is going to be equal to 1. So if v1 indeed belongs to our image, it's enough to show that the intersection is non-empty, so the intersection lies some non-zero vector, and then from this argument the dimension are equal to each other, I'm going to exactly get that my vector v1 is going to span the image of a minus lambda I. So in other words, I want to show that the first case is impossible. Okay, so let's show this. Assume kind of by contradiction that this is possible. So we need to remember that since the dimension of image of a minus lambda is equal to 1, and the intersection with the kernel is going to be a 0 vector, then it means image of my linear transformation is going to be spanned by some vector w, and this w doesn't belong to kernel. So then we can see that if we're going to take any vector like w prime, then the image of this vector w prime is going to be just w times some constant a. But then what I can take? I can take w prime is equal to w, and I will get a minus lambda, sorry, not lambda, lambda in this case is equal to 1. W prime is w, so it's equals to aw. So from here I'm going to take this minus I times w to the right hand side, so we'll get aw is equal to a plus 1w. And remember, when we chose our w prime is equal to w, in this case we assume that a doesn't equal to 0, because if a is equal to 0, then we have that a minus I w is equal to 0. So from here follows that w belongs to the kernel of a minus I, but we assume that w doesn't belong to a kernel, so that's why a doesn't equal to 0. But I'm going to obtain contradiction. And why do I have a contradiction? Because in this case we can see that w is an eigenvector, and but according to our step number 1, we have the only eigenvector which has an eigenvalue is equal to 1, and this eigenvector is what? Is v. So from here follows that I must to have a is equal to 0. It's our first contradiction. And second, that v lies in a span, sorry, w lies in the span of v1. And this is also a contradiction because w doesn't belong to the kernel. So the first case doesn't work. And from here we have that kernel of a minus I intersection image of a minus I is not 0. And here we don't have lambda. Lambda in this case again is equal to 1. Okay, so what I'm doing right now, I'm trying to show the part number 1. And what I got, since v1 belongs to the kernel, and according to our computation, if some vector w is going to belong to our image of a minus lambda I, and in this case the intersection is non-zero, then this vector w is going to lie in a span of v1. But if w lies in the span of v1, it means we can choose w to be equal to v1. So from here follows that v1 belongs to the image of a minus I. So right now what we did, we figured out the algorithm how to find our vector v0. So as a step number 3 right now, actually compute the Jordan form for A. And how we're going to compute? We're going to find our basis B prime, apply the change of basis matrix, and then we're going to get our Jordan form. So the first idea that we're going to start with basis B, E1, E2, and we're going to change this basis to a new one, B prime, which is V0 and V1. So as a step number 1, let's find V0. According to our discussion, it's just we need to solve the following system of equations. A minus I V0 is equal to V1. And remember that let's choose V0 to be equal unknowns A and B. We know what is our V1. V1 is equal to 1 and 1. So from here follows that I'm going to obtain a matrix 1 minus 1, 1 minus 1, which is equal exactly to A minus I. AB is equal to 1 and 1. And from here I'm going to obtain that A minus B is equal to 1 and 1. So we can see that A minus B is equal to 1. So from here I can conclude that A is equal to B plus 1. So we found the general form for V0, and we actually found not only one, we found a lot of vectors of V0, which are exactly B plus 1 and B. But for simplicity, I'm going to choose B is equal to 0. So I'm going to fix our V0 to be equal to 1 and 0. Okay, so here we found our vectors are going to be 1 and 0 and 1 and 1. So as the last step, we right now need to figure out how the change of basis matrix works. So here's our space R2 with basis B, and it maps into our space, the space R2 by our matrix A. But what can I do? I can do a change of basis matrix P, and I can do the change of basis P over here. And when I do a change of basis matrix, I'm going to obtain another matrix, and this is going to be exactly our matrix G. And from this diagram is going to be computative. You can see that to compute our G, we need just to compute P inverse A, P. And why is this true? Because if I want to take some element V here, and I want to map this element to R squared over here, instead of using this G arrow, I'm going to first apply P inverse, then A, then P. And this is how I'm going to, in other words, trace my element by using this commutative diagram. So we're almost done. The only thing that we need to do, we actually need to compute our matrix P. So to find matrix P, we just need to remember that our old basis was B is equal to E1 and E2, and our new basis B prime is going to be equal to V0 and V1. But we know that V0 is equal to 1, 0, so it's just equal to E1. And V1 is equal to 1, 1, which is exactly E1 plus E2. So matrix P are going to consist of two columns. When in the first column, I'm going to put the image of the first basis, which is E. And for the second one, I'm going to look for the image of E2. But here we can see that E1 is going to be just mapped to E1, which in this case is just V0. And E2 is going to be mapped to V1, but V1 is just E1 plus E2. So our first column is going to be just 1 and 0, because I can rewrite E1 as 1 times E1 plus 0 times E2. And our second column is going to be 1, 1, since I have 1 times E1 plus 1 times E2. So from here follows that our matrix P is going to be equal to 1, 0 and 1, 1. And finally, we can figure out the matrix G right now, the Jordan form of the original matrix A, where our A was equal to 2, negative 1, 1 and 0. So according to the formula, our matrix G is going to be just equal to P inverse A and P. Quick computation can check that P inverse in this case is going to be equal to 1 minus 1, 0 and 1. And the reason is why, because if you're going to multiply P by P inverse, you will get the identity matrix. So in this case, what do I have? I have 1, negative 1, 0, 1. times 2, negative 1, 1 and 0 times 1, 1, 0, 1. And let's multiply those matrices out and see what we're going to get. So the first multiplication, like these two matrices, will give us 2 minus 1, which is 1, times 0 times 2 is 0 and 1. The second column will give just negative 1, and the first component is going to be just 0. And I'm going to multiply this matrix by matrix 1, 1, 0, 1. In our last computation, we can check that I'm going to get for first entry 1, for the second entry 1, 2, I will get 0, then I will get 1 and 1. And voila, we actually got the Jordan form, which is going to the block diagonal as we predicted before. So as an exercise, I recommend you to try to practice the same approach for the matrix 1, 0, 2 and 1. And please let me know if you have any questions about this exercise. Okay guys, thank you for watching this video. If you're not subscribed to this channel, please subscribe. Let me know if you have any questions and if you want to see when I'm going to apply the same approach for 3x3 matrices and etc. Have a nice day. Bye bye.